Once we start being able to do synthetic problems, then it's going to be really useful for you to have a good carbon-carbon bond forming tool. And at least for the early parts of synthesis, what you really need is alkyne chemistry coupled with SN2. So now that we've shown you SN2 and acid-base reactions, now you're ready to learn the key tool that you're going to use more than any other to build carbon-carbon bonds. So fundamentally, what you're going to take advantage of is an SN2 reaction, but before you can run the SN2 reaction, you always have to start by running an acid-base reaction with an alkyne to get this ready so that you can perform synthesis. And the upshot of this two-step procedure here is that you end up adding a new 2-carbon chain to the end of your molecule. So in other words, this alkyne, you end up running an SN2 reaction, which cuts right there and installs an ethyl group at that position. So how does it work? First, we run an acid-base reaction. We follow that up by throwing in material for an SN2. So this really takes advantage of the fact that this CH bond has a pKa of about 25. There are plenty of bases that we can use that have pKa's of about 35 or higher, so we can go ahead and cause that to deprotonate at will, and then we can throw in the material for the SN2 reaction and allow it to proceed on for synthesis. So your primary toolkit right now is going to be using these alkynes like acetylene in synthesis, and so what that means is it's always possible for you to add 2-carbon units at will, and so you should be on your lookout for those as you're trying to think about synthetic routes. Okay, so how does it work? Well, we have a carbon-hydrogen bond which, when deprotonated, will lead to a minus that's held in an sp hybridized orbital, and that's relatively good, so that minus will be relatively close to the nucleus, which means that this is a relatively low pKa. Sodium hydride is a base that you can use to cause this transformation to take place, and I've often told you that when you see sodium, you should think of it as being largely sodium plus, and often as the other thing minus, and this is kind of the exception to that case, where I'd really prefer you draw it as sodium hydride, as an actual covalent bond there. Having said that, the way it's going to behave is, of course, very similar to what I've described previously, with the sodium being sodium plus and this being H minus. The problem is, I don't really ever want you to draw H minus, because H minus is one of those things that really doesn't exist. So think of it instead as this bond coming and doing this reaction, which will then cause those electrons to now sit in the sp hybridized orbital. Once this deprotonation has taken place, this really is a carbon minus now, and that's just sitting there, and the sodium plus is sitting nearby. But this is something that is going to happen relatively quickly, and it's also something that's going to happen entirely one way. And that is because if you think about what the byproduct is that you're generating here, it's hydrogen gas. And so hydrogen gas actually boils up and out of your system entirely. So this is, because of the 10 to the 10th difference, a very product-favored reaction. But in addition to that, the product literally leaves the vessel. It actually boils off, floats away, and therefore it cannot go back the way it came. So sodium hydride is an outstanding choice of a base to use when you would like to deprotonate and just have the hydrogen gas go away. It drives the reaction to completion. Even if it's a relatively balanced equilibrium, this fact that it's boiling away would still cause the reaction to go to the right anyway. So anyway, this will then form the desired anion, and now you will have your SN2 type substrate floating around nearby. This will then come and displace the iodide as expected, and that then leads on to your final products. And once again, this is going to be a one-way step, because carbon minus is a terrible leaving group. So this is a process that's all one way and ends up right there. You should be advised, however, that this really requires a primary substrate in order to work. This will not work if you try it on a secondary substrate, and though at the moment you may not realize why, as soon as we start talking about E2 chemistry, you're going to start to realize, yeah, of course, this makes sense. So primary substrates you can do this kind of reaction on. Secondary substrates, you're instead going to do something else, elimination, rather than what you want to have happen. Main synthetic tool for your toolbox, do some kind of deprotonation on an alkyne, so it has to be a terminal alkyne. It's got to have a CH bond on it. Once you pull that CH off and you have the full-on minus left behind, you can throw in a primary iodide and it will displace it and lead to your desired products. So what are the kinds of bases we can use for this? Well, I would say that tool one is sodium hydride, and the main reason for that is it's got a pretty good pKa of about 35. It's reasonably cheap. It doesn't generate a whole lot of waste. The main product you're generating from the reaction is hydrogen gas. It boils off. There's really no reason not to use it, except that you can start fires relatively easily this way. On the other hand, these are pretty reactive bases as well, so it's not like you're avoiding the fire hazard entirely. Sodium amide is another option. It too has a pKa of about 35, give or take. So it's a relatively strong base and relatively small, and this will work just fine. LDA is another base you should be aware of. It's huge, very, very bulky, and it's stronger, so you can use this instead. And so what you have is now this diisopropyl amide and the associated lithium. With the sodium hydride, I would want you to draw it as sodium hydride covalent like that. With these, it's fine to draw them as their ions. And once again, what you use is one of those bases in the first step to cause this to deprotonate and generate in situ, which means in the same flask, this minus charged material, which you never draw. And then in your second step, you add in a primary iodide or other primary halide and some SN2 friendly solvent like DMSO or DMF, and that causes the reaction to go.